The third method of representing signed binary numbers so that we can perform binary arithmetic is what we have already introduced as 2's complement. A 2's complement is a derivative of 1's complement, and we say that the 2's complements of a number is obtained simply by adding a 1, that is a binary 1, to the 1's complement representation of that number. So we have already seen how we can generate the 1's complement of a given number. Once we have followed that procedure to generate the 1's complement, all we need to do is to add a binary 1 to that number, and we end up with the 2's complement. In general, the r's complement of a base r number is the sum of the r minus 1's complement and 1. So that is quite simple. So in the decimal number system, we said that the r minus 1 equivalent is 9's complement, and therefore if we were to find the 10's complement, which is obtained by this one we are saying r minus 1 is equivalent to 9's complement. Therefore, the r's complement is obtained as 9's complement plus 1 becomes 10's complement. Therefore, the same method would be followed for the binary complement, because with binary we have 1's complement, which is equivalent to r minus 1. And therefore, when we have r complement, this is equivalent to 2's complement, and it is obtained simply by taking the 1's complement plus 1, and that becomes rather straightforward. So in the decimal number system, the r's complement is referred to as the 10's complement that I already mentioned, and the best way to learn how these 2's complement work is via an example. So our example says that we need to obtain the 2's complement of these binary numbers. So we are given this is the first binary number, is the second binary number. And if you just recall very quickly, the 1's complement of this number is obtained simply by interchanging 1's with 0's and 0's with 1's. So I will do that to obtain the 1's complement. So 1's complement is given by 1 1 0 1. So that is how you obtain this becomes 1, 0 becomes 1, and 1 becomes 0, as we can see in this example. So this is the 1's complement of this binary number. Therefore, to obtain the 2's complement, we simply add 1 to the 1's complement, and that becomes 1 plus 1 is 0, carry 1. 1 there, 1 plus 1 becomes 0, carry 1. 1 plus 0 is 1. Everything else remains the same. 1 0 0 0 1. So this is the 2's complement of that number, and we can follow the same very simple procedure to obtain the 1's complement for this other example. We obtain the 1's complement first, interchange 1's with 0's and 0's with 1's. This becomes 1 1 1 0 0 1 0. So that is the 1's complement. You add a 1 to obtain the 2's complement. You become 0 0 0 0 1 0 1 0. All I have done is to add 1's all along here. They become 0's. You keep on carrying 1. The 1 comes here, so that this is where we obtain 1, and this remains as 0 1 0. So the 1's complement or the 2's complement for the second example is simply that, and the 2's complement for the first example is simply that. So in summary, we can see that we have done the same thing like I have explained in the example, and you can see that this number is the 1's complement that we obtained here. So this is what we find there. That was the 1's complement, and then when we obtain the 2's complement, we are able to verify that this answer that we found here is this same one that we have found there. And similarly for the example 2, the answer is as illustrated. So we continue with the 2's complement and say that some simple rules can be used to obtain the 2's complement from the binary sequence as follows. So there's some quicker method to obtain the 2's complement. So we just need to check the position of the least significant 1 bit. So if we are given maybe a number, we just need to check which is the least significant bit 1 in the given binary sequence, and then we complement all the bits to the left of that least significant bit So for instance, we are given 10101111, or I think I would rather have some zeros there. So if you are given such a number, you want to obtain its 2's complement, the least significant bit, one bit, is this one. So you leave this uncomplemented, and then you complement all the others. So you complement all these others, and that way you obtain the 2's complement. That is what we are saying here, that you complement all the bits to the left of the least significant bit. Therefore, zeros become ones and ones become zeros, and then the least significant bit itself is left and complemented, as well as all the bits to the right. So for instance, for this one, you'd simply get 0 1 0 1 0 0. These are the bits to the left of the least significant one bit, and from that least significant one bit towards the right, you leave them uncomplemented. So this is the 2's complement of this number. So this is the given binary sequence, and the 2's complement becomes this one. Very simple procedure, much easier even than the one for obtaining the 1's complement. So another example for this 2's complement, we use the 2's complement rules to obtain the 1's complement, to obtain the 2's complement of this number. So we have said that we just need to look at the least significant bit 1, and you can see it is this one. So we will not touch these two. To the right, you don't touch them, then you complement everything else. So this becomes 0 1 0 0 1 1, and this one remains as 1 0. Clearly that is the 2's complement of that number. So we make some summary and say now that in the 2's complement scheme, positive numbers are represented by the binary equivalent. Just like what we said in the 1's complement, we don't complement a positive number. All we do is to add the most significant bit to 0. So if we are given maybe any number like 101, like we did, you should always add a 0, and this one is already in the form that it should be, for that to allow us to perform the sign bit arithmetic, be it addition or subtraction. And we say that a negative number is represented by the 2's complement of the corresponding positive number. And this means that the most significant bit of that number should always be set to 1. So like we did in the previous lecture, we had 37. We represented it as 1 0 0 1 1. This was 32 plus 4, 36 plus 1. So this is how we represented 37. If we want to present it using the 2's complement, you should just let it remain as such. Or if you are to do binary arithmetic using the 2's complement method, just leave the 7 as it is. All you need to do is make sure that the most significant bit is a 0. Therefore, if you are to represent negative 37, we just complement this number, and when you complement, the leftmost or the most significant bit will become 1, and all the others are going to be complemented as we have followed the procedure. So we have an example here. We are to do 2's complement of plus 42, and similarly like we did, we just know that the number that is the multiple of 2 that is less than 42 is 32. So we have 32, we cannot add 16 because it will be bigger than this one. So we will have 32 plus 8, we get to 40 plus 2 plus 1. This becomes equivalent to 1. 16 is not represented, therefore 0. 1, 4 is not represented, then 2 and 1. This is our 42. Therefore, if you had used the 8-bit scheme, we count that these are 6 bits. What we need to do is to precede these 6 bits with 2 zeros, and the 8th one, which is the most significant bit, will need to be 0. Therefore, to obtain the 2's complement of this number, you can just use the same method, which simply means you're going to complement all the numbers except the least significant bit 1, and therefore we'll obtain 1 1 0 1 0 1 0 1. Therefore, this becomes equivalent to the minus 42. I think I made a mistake here. This should be okay. So that correction is made. So it's supposed to be like that. So the most significant bit here should be this one. Therefore, it will not be touched, and therefore the final end result will be 1 0. And that is how we represent negative 42 using the 2's complement. Again, in summary, we say that in an 8-bit scheme, 0 is represented by a binary sequence of zeros, as we can see. And if we were to do a -0, we would still obtain the same, because there is, if you follow whichever method we are following, if you are to change this to 1's complement, it will become 1, 1, 1. And then when you add a 1 to get the 2's complement, everything else becomes a 0. So we can see in this method that unlike the sign magnitude and the 1's complement scheme, the 2's complement provides a unique representation of 0. So it doesn't have two methods or two representations, and therefore this one is a better method of representing signed binary numbers. So as much as we have gone through the two other methods, that is the sign magnitude and the 1's complement, those have their disadvantages and they are undesirable, particularly with the dual representation of 0. But we have seen that the 2's complement provides a superior way of representing, or a unique way of representing 0, whether positive or negative, and therefore this makes the 2's complement suitable for binary arithmetic operations. We say that in binary addition, using 2's complement, the two numbers to be added are expressed in the usual binary format if they are positive, and in 2's complement format if they are negative. Further, the most significant bit must be a 0 for a positive number and a 1 for a negative number, that we have already seen. When both the ANDed and the AUGed are positive, the binary sum is also positive and has a most significant bit of 0. The magnitude of the sum is obtained directly using the usual method of binary addition.